So first of all, welcome to all the other panelists besides Cleve. So let me introduce you to Klaus Dippold from Electrical Engineering. Welcome. Then I skip over for a brief moment and say welcome Florian Holzapfel from the Mechanical Engineering. And then it's a special pleasure for me to introduce you to my PhD supervisor, Manfred Breu, from Computer Science. Great. So just for you to recognize these folks, my name is Joachim Schlosser. And yeah, let's kick off this conversation about a question to basically all of you, and we may sort out the order of which we're answering it. So what role, maybe starting with you, Cleve, what role really did computer science, if that already was a word back in the time, play in other sciences when you started first?
Well, I don't want to talk. I want the other people to talk because I've been talking a lot. When I started first, computer science played no role because there wasn't a computer science department yet.
Good, and this was important that we have this answer because we now can move to maybe you, Klaus Dippold.
It was pretty much the same when I started. At that time, there was still no computer science department. It was still a part of mathematics. In that sense, from an engineering perspective, we went there to take classes in Fortran programming with the cards still, and so that was the beginning. At least when I was a student, computer science was, well, not really visible from that perspective, except for Fortran programming.
When was that?
81.
81. So then the next obvious thing would be to ask the same question to a computer scientist.
Well, I'm a bit amazed because I think already in the 70s when I studied, it was obvious that computer science was used in a number of fields. For instance, if you look at Bosch brought in, and that's good because you mentioned Volkswagen, Bosch brought in the first little bits of software into a car in the beginning of the 70s. So at that time already things worked like that, and I think there are a number of fields like that. We were at a time where I think telecommunication was going through a revolution because we went to those switching systems which was controlled by software. So I think in a number of disciplines, computer science had a role, but it was very much in the technical disciplines, sometimes embedded systems, but also in that time you have to think about that also DARPA was working towards the internet, and that was in the 70s. So there was a lot going on, but it was not very visible. When I studied, a computer scientist was wearing a white coat and sitting in a center, far away from the people, and everybody thought that this is nothing which has to do anything with reality. My supervisor, my PhD supervisor was mentioned, which was Fritz Bauer, who passed away just a few months ago, and I talked to him several times over the last years to find out whether he had any idea what computer science would develop to when he was doing his work on algol and stuff like that. And he said, no, not at all. I think we all are amazed by what's happening there, and that we now see computer science everywhere.
And now, computer science on the one hand and math on the other hand. Florian, what role does math really play in engineering today?
Well, I think math always played an important role in engineering, but one thing that changed over the time, and this is now a mean statement, something like 20 or 25 years back, you fully had to understand the math in order to being able to utilize it for engineering tasks. And now, thanks to tools, you have more and more possibility to really focus on the engineering work without the requirement to fully understand the math. And something like 10, 15 years back, I was of the opinion that it's so important before you apply something, you completely understand what's behind it. But in the end, if you look today, there are a lot of kids doing things where many professors would say, oh, these things are completely impossible. And this is because they completely focus on the project and they are not burdened by the load, that they have the feeling that they should understand everything. When I had my first computer, it was very far back. It was, I think, in 1981. Then if you wanted to add two numbers, you had to load one number in the accumulator and then load the other number in a register and then put them together. And so I, for a long time, had the opinion that to operate a computer, you need to understand it. If you today ask anybody playing around with a cell phone, if they know what happens behind the cell phone, they don't know, but still they can use it. And I think slowly the same starts to happen also with more complex methods. If you would require the people to fully understand all the methods which they use in their everyday work, they would have no time to do their everyday work.
And how does that relative importance of math still come into computer science? Manfred?
Well, I think when I started, computer science and math were much closer together than they are today. If you look historically, it's interesting that a lot of computer science came out of math, but mathematicians at that, besides the numerical mathematicians, they were different. But the rest of the mathematicians decided not to consider computer science as their engineering discipline. And you can see how that happened in the departments. And the result was that computer science, or informatics as we say, split away from mathematics and became its own discipline. And therefore I think today there's a lot of mathematics in computer science, but there's a lot of computer science which is far away from mathematics. And I think we have to become aware of that. And perhaps it's not even true, but it's a lot of mathematics in computer science which is not the mathematics mathematicians developed. So we have developed our own mathematics. And if you look what we are doing today with all the structures and protocols and stuff we have in our field, there's an awful lot of mathematics, but of a completely different kind. And it has to do with logics a lot. And when I studied mathematics in this university, and I didn't learn anything about logics when I did that. And only later when I worked as a computer scientist, I learned about logics. And so it's interesting to see how things are related. And Cleve mentioned Turing. And I think it's interesting to see the work Turing did in logics. And so our roots are much more nowadays, as we understand it, in logics than in numerical mathematics. And that makes a big difference.
And Cleve, you also mentioned when you gave that class in Stanford that the computer scientists and the maths people were not so intrigued by what you were showing them in Matlab, but the engineers were. How do you think does relate what we just heard now back to the experience then? Is it still the same then, or what have you seen changed?
Well, at Stanford, that course doesn't even exist anymore. There is no numerical analysis class in the computer science department at Stanford. The computer science department at Stanford has become quite theoretical and has nothing to do with numerical analysis anymore. There is some numerical analysis department going on in the math department. Some numerical analysis going on in the math department, which is a complete reversal from the situation when I was there. We have to distinguish here between academic computer science, which is a quite theoretical, abstract discipline, and what maybe you were talking about, Manfred, what computer science in general, which is people working with computers, and what goes on with people in industry, so on, that are thinking about computers and so on, and computational science, which is a different business, and system science and so on. The computer people in computer science departments today, many of them don't go near computers.
True. They for sure do in electrical engineering, as far as I'm aware. So, what role does math and also computer science play today in electrical engineering?
Well, I think maybe fitting to the event today, I would say MATLAB had certainly, or a tool like MATLAB had a profound influence on how math should be taught in an engineering class or an engineering program. So if you go back, and we still do this most of the time, classical engineering mathematics, which is more like recipes on how to calculate stuff. Not necessarily looking into the details of the structures, and most engineers don't even know how to craft a proof. And traditionally, the education in linear algebra was only used as a tool to solve differential equations, or ordinary differential equations with constant coefficients, so very fundamental stuff. So, and students have been wrapping their minds around of doing Laplace transforms and analytic functions and all sorts of things like this. And with the advent of MATLAB, all of a sudden it was not so important to know exactly by the tables how to convert a polynomial or a series into what a function this is and so on. You just punched in the MATLAB, the coefficients into MATLAB and asked for the solution for the roots of this polynomial. And when I was a graduate student, it was still the primary task of every first year graduate student to write a program in Fortran, notably, to solve polynomial equations for looking for the roots. And those things nobody has to do anymore because you just use MATLAB for that purpose. And all of a sudden that means you also have to think more in terms of linear algebra to make use of MATLAB in a more efficient way. And that is, I think, a profound shift that we can see in engineering education, that we're going away a little bit more from the traditional calculating recipe mathematics to a more profound understanding of what is linear algebra. And once people understand what a singular value decomposition can do for you, you also may want to demonstrate it with MATLAB, and some people in advanced level even want to know how it works. So I think this has been a major shift, and I'm not so sure if students do not have to understand maybe the mathematics. They may have to understand a little bit different mathematics than 30 years ago. I fully agree with that part. But so the first time for me and for my thing with the students before me, computing a Fourier transform was always like Alice in Wonderland. You're living in time domain, you jump through a hole, and all of a sudden you're in this miraculous frequency domain. You don't even know what this is. Today, you can use MATLAB and you punch in FFT in a time series, and then you can see the spectrum, and it becomes much more graspable and much more realistic. And I think that those things are a major shift, and it still continues. That the computing part becomes more important than it used to be.
But Florian, does that mean that students also understand better, let's say, the frequency domain than back in the days?
So what I think is most important for engineers is to intuitively understand the physical concepts behind something. So in order that things get tangible, so when they see frequency domain things, it should have a real meaning. But if you look at it, then this meaning does not come from the transformation formula, but it comes from the interpretation that the physical everyday life is well connected to what you see in the depiction. And then, of course, it's a big benefit if you can bring your everyday experience in a very simple and straightforward way to this other domain, so you learn to interpret the things. But once again, I think this understanding comes from bringing together the artifacts in other domains with what you know from your physical everyday life, which is not necessarily coming from proving the Fourier integral.
Now, reflecting that, this very concept of thinking in different domains, back to you, Cleve, how did you perceive the usage of the very, very early MATLAB, even before it went commercial, by different domains? How did you grasp the different domains, and what did it do to your perception about the usage?
Well, before it went commercial, the usage of MATLAB was entirely in matrix computation and just doing simple matrix tasks, just in the business of this matrix laboratory. It was. I can't remember that there was much outside that domain, and there it was just. I mean, it was almost true that I knew everybody that was a user, and it was only after we we got hold of after Little got hold of it, and after engineers began to get hold of it, and this crazy business of control theory showed up, that we began to get more interesting things. I didn't know about the frequency domain until these people showed up.
Yeah.
It's an eigenvalue decomposition.
So you say, but I didn't understand. I didn't have the physical feel for it that you were talking about. If you just say it isn't. If you say it's an eigenvalue decomposition, you're just talking about the mechanics of it. That doesn't give you any idea of what it really means.
That is completely true, but I think it's the linking between the two things. You need to understand what the physical reality is, what it reflects on, and also know what it corresponds to in terms of the tools that are available to you. So if you have a physical intuitive understanding, but you don't know what the computational tool is called that you may want to use for that, then you may have a problem. So I think that it's the connection between the two things that really makes it work.
If I tell somebody, that eigenvalues are the roots of the characteristic polynomial, that doesn't give you any understanding. If I tell you that it's vibrations or resonance of a swing or something, that tells you what eigenvalues are.
So I perfectly agree, and this is why I think you have to explain eigenvalues to engineers in a different way compared to how you have to explain them to mathematicians. And so it's my opinion that basically over time work is split up more and more, right? And something like, or still 20 years back when I was a student, basically you need to have very good programming skills in order to use a computer to solve your problems, which of course moved you away from your problems because you had to put a large focus on programming, right? That was distracting you from tackling the original program. And I would now say that the work share gets more because you have people providing tools and methods, and you have the other people that can have their mind free and put more focus on the application, which means that now you can do things in application that have not been possible 20 years ago because you did not have this free part in your head, which now can fully focus on the system and on the application.
I also have to explain that eigenvalue is a word that we only got half translated from German. It's like liverwurst.
Yeah.
But you fired back with singular values.
Yeah. And
actually, I must say, I'm missing one word in the discussion, which is modeling. I think the real question there is, if we look at the physical or whatever thing we observe, then we want to understand it. We use models, and of course mathematics is just giving out a lot of models, but there are a lot of situations where we wouldn't use typically numerical models in mathematics. Cleve talked about the refugees. An interesting question is what's going on in the information flow we have with the refugees. Because I'm convinced we wouldn't have refugees as we have them today without computer science or without the internet or without smartphones. And therefore there's an awful lot of interesting stuff going on when those people communicate and how they inform each other. And now think about how to model that, how to find an understanding of what's going on there. And then you have to go into models. And I think there are many, many interesting models. And the interesting question is, which of the models reflects what's going on in reality the best? And the same is true for matrices. Matrices are just a mathematical concept. But whether the mathematical concept applies in a particular situation, that's quite different.
So this is interesting. So the refugees are our fault. So they're the internet's fault or the cell phone's fault. We wouldn't have them without?
No, I'm not saying that. I'm saying the dynamics you find in the field of refugees is deeply influenced by the information flows that these people use. And I don't have data about that, but it would be fascinating to understand how that is reflected in their behavior.
Yeah, so tapping into telecommunications and finding out more.
Yeah, if you look at social networks, and there's some work going on in modeling the behavior of people in social networks. And I think so there's much more. We had this title about computational thinking. I think I know the term, and I discussed a lot with American colleagues, but I think the term is wrong. It's not so much the computational thinking, it's first of all the modeling with techniques that allow us later to do computations on that. And I see the modern form of computer science very much as a discipline of modeling and being able to make the models in a way that you later can calculate with them in computers. And then numerical models are just one part of it. And there are lots of other models which are highly interesting there.
And the concept of modeling also becomes more and more important in engineering, as we learned. I mean, Cleve, you saw it today when visiting Florian's chair. There was a lot of modeling going on there with all the Simulink models that you saw, and even the very flight simulator that Cleve was sitting in. Florian, what does modeling mean to you in your field of research and teaching?
So basically, the more complex and the more expensive a real-life system is, the more you want to make sure that nothing goes wrong. And so basically, modeling is just a way to get an early abstraction of what you're planning to do. And so basically for us, it's the basis of doing our stuff, because we cannot do everything experimentally. So basically, I would say that we as engineers have the domain knowledge to find out on how to create a proper abstraction of the reality, which is just as complex as you need to solve a certain problem. So something like 15 years ago, I was thinking the best model is always the one that has the highest fidelity. Now I would say this is completely wrong. For a good engineer, I think it's important to find out what is the level of abstraction you need from your real system to put it into something which is computationally accessible, that is just suitable of doing the job you have to do. And so this is the very basis of our doing, and you can do it wrong by not hitting the right level of fidelity, be it to be too low fidelity or too high fidelity. So our knowledge is the domain know-how on what's the right model, and because once you have the right model, then the computer people deliver us with the methods which we can use to work on those models.
And now, translating the increased use of models and also the feasibility to calculate more with models, I want to step back a little bit and say, you all have seen tremendous innovation in the last decades. What, in contrast, Klaus Diepold, do you feel has stayed the same in the challenges for your field?
Of course, there's, if you just go back quickly for thinking about computations, of course, there's always a certain amount of questioning about how to reduce the amount of computations and the time and the resources needed to get to a problem solved. And that is, I think it is the same if you are modeling, if you do a simulation of electrical circuits or dynamic systems. And it's also a key element of consideration if you're building embedded systems where the numerics and the computations are not just the means to model and simulate, but it's the mechanism, it's the true thing by itself. So you build a system where the heart is a computer that receives signals from the outside world, and it produces something internally by computations, and it produces something that has meaning into the outside world, interaction. So computation is the element of the product itself and not just the means to simulate. In that sense, engineering means you want to accomplish a certain task with the minimum amount of resources necessary to achieve a given quality level. And in that sense, I think that's still the same. Going even back to the time of Wilkinson, when you want to find out, okay, how you can save computations, and even the parallel world has tried to save time, at least with for the benefit. So I think being greedy in terms of computations is a kind of constant.
Okay. Cleve, what is your feeling has stayed the same?
Explaining to the rest of the world what we're doing. People have no idea what I do. You see programs on television all the time with interviews with astronomers. Astronomers get lots of time on television and lots of specials on Nova and so on. You never see mathematicians. We just don't we get no respect, as Rodney Dangerfield used to say. It's hard. It's hard. Physicists and chemists maybe sometimes, but no. I mean, I've been worried. We don't telling people what we do. We do important stuff, and the rest of the world needs us. But it's very, very hard. And people keep saying, you know, I say I'm a mathematician, and they say, oh, algebra was my worst class in school. And that just ends the conversation there.
Yeah.
Yeah.
But maybe you can gauge the importance of a field by how often they appear as the heroes in a TV series or show. So the engineers always complain there's hardly any engineer, a hero in a movie or in a show. There are physicists, of course, they're crazy and creative and they're the super brains. And the mega brains are the mathematicians. They can flip pens like crazy and do funky stuff. But engineers are just like Scotty from Enterprise. Right. Scotty says, well, the power shields are down by 30%. And then the captain says, fix it. And he said, oh, okay, we're going to fix it. But nobody knows what they're doing, and the heroes are the physicists and the scientists. Spocky is the hero, and even the medical doctor is so in a social ranking in front of the engineer, because McCoy has more time to talk to the audience than Scotty. And Scotty always gives just like the keywords for Captain Kirk to come up. So the mathematicians are certainly not part of this Enterprise.
Yeah, there's no mathematician on
But you see the picture. But the pictures, you see the singular values in
yeah. And on. What's the popular one now with the
Big Bang?
Big Bang
Theory.
There's no mathematician on there.
And the engineers are the idiots.
Right.
So,
and no computer scientist.
We're going off on a tangent here.
It's his choice if it's better to being paid for being invisible or for being paid for being an idiot. So.
Yeah, matter of choice. And so to stay in your terms, to fix the lack of awareness for mathematics and maybe also computer science, is that one of the reasons for the founding of the Center for Digitalization in Bavaria? Professor Breuer?
I think in computer science it's a bit different because if you look at the field, we have a number of computer scientists, maybe I shouldn't call them scientists, but computer people that have a lot of attention. You mentioned Bill Gates. Think about Steve Jobs. I think things have changed a bit. We can debate for a long time whether we like it or not, but I think computing as a discipline has really left its laboratories. We find it everywhere, and people understand this is of a very high value and of economical importance. And of course, Zuckerberg is certainly not a scientist, but he certainly is considered as a computing person. And therefore, I think things are really changing. We are going into a world which is really full of digital technology. And to what extent digital technology is related to what we were talking about today is an interesting question. It is part of it, but it's much more. And I think this is a development which is really amazing. It will change the world. And if you talk about what we do in Bavaria now, we really try to understand what's going on there and what it means for the people, for the companies, for the politicians. It's a big, big change. And you were talking about that people perhaps do not understand what they are using, but they use a lot of this technology. I think they don't have to understand if they use their smartphones, how the addition is done in the machine. But I think they have to understand an awful lot of things in addition, because if they have to understand if they put data there, what's happening to the data and how dangerous it is to do it and who is observing what they are doing. So it's a completely different level. So but what I find fascinating in my discipline is when I started, computers were in labs. A little bit later, they were on our desks. Then they were on our laps. Now they are in our pockets. And we are close that they will be in our bodies, and they will be everywhere. And I think this is a much more challenging question, how we deal with that. And that's what we think about in Digital Bavaria.
You're talking about how how you've seen computers. What's amazing to me, I mean, computers are the same thing has happened to me, of course. Computers have been in my life forever. But what's fascinating to me is how much they've shown up in everybody else's life. Like my mother-in-law, all right? My mother-in-law loves email. She says every email is like opening a present. She just waits for email from all her kids, right? So she never had anything to do with computers until just a few years ago. And that's just fascinating. That out in the hills of Western Virginia, she has a wire coming through the trees to get into her house so she can get email. That's just, and now I see URLs on trucks, you know, plumbing trucks. Who expected to see so-and-so hvc.com, you know, on a truck? The URL was never designed to be showing up on the truck or on the tail of an airplane, right?
Yeah, but that's really fascinating because I started to work in the field with Fritz Bauer, and he was an American analyst, but at that time he already developed into somebody who was much more in the broader field of computer science. And that's what we see today, but it goes beyond the imagination of everybody who was in the field at the time.
Yeah.
And it's moving very fast. And I think it's interesting to understand that. And I was at the MathWorks Summit this year, we met there, and I was fascinated because it's clear that if you look at the MathWorks you introduced, how you started it, this was a very limited part of modeling in mathematics and engineering. I learned now that MathWorks looks to understand how this relates to a much broader thing. And take one example, we work a lot with the German car industry. And then, of course, they use awful lot of MathWorks, but they use it in very special parts. So they look at control functionalities. There's a higher level in a car where you do orchestration. And it's no longer at the level of the classical control theory. It's a different level.
Where they do what?
Where they do orchestration, because now you have all the functionalities, how you do the brakes, how you do the acceleration and so on. But then there's a level where you really do, for instance, in an automotive driving car, you decide about what to do. And this is beyond control theory. It brings in completely new questions, and I find that fascinating. I see that everywhere, that we have this kind of a stack of different technologies, one put on top of the other, to achieve what we see today in these powerful machines. And if you would take a smartphone and you would beam it back, because you talked about science fiction, you beam it back, and it would give it to me 30 years ago and would say, this, look, I wouldn't believe that. I would consider it as a miracle. And so what we have seen is unbelievable. And it's based very much on work you were talking about today. But in a certain sense, it goes into a breadth in development which is unbelievable. And we will see more of that.
And the question that comes to my mind, especially when looking to this academic audience, also built up of students, is to deal with that very breadth and that evolution. So in your teaching, how did and how do you handle the stretch between the evergreen foundation, the mathematical foundation, and the advances in computing and the changing context?
Well, in my space, I would say, well, the mathematical concepts have to be kind of going hand in hand with the computational implementation, working with the tools at the same time, not just pencil and paper. Get your fingers on the keyboard, make it computable, and experience it. As you said, you have to see the consequences of what those mathematical models and tools, what they mean to you, and that you can now experience much more vividly than you could do 30 years ago or before the time of Matlab, because now you have the tools available to see immediately what happens. And I think that's an important element of teaching, seeing the connections of both things. Absolutely important.
Good.
So I think this is exactly the point, that in teaching you always have to make sure that there is a sound balance between the theoretical background and the application. So you can see the theoretical background as the horsepower, but if you don't have any transmission to get it to the road by itself, it's worthless for an application. And so basically I would say that if you look at the curriculums in engineering math over the last 25 years, they stayed pretty much constant, but what significantly improved is the possibilities you have to show and demonstrate what this is useful for, because you have efficient ways to directly demonstrate it when you teach it.
Cleve, also in your teaching, how did you deal with that stretch between teaching the mathematical foundation and really using advanced programming techniques?
Well, it's been a long time since I've been teaching, but I mean, they were always to me they were always close. I mean, I was always teaching about what I was computing. So in the stuff I was teaching, I certainly made it a point to make a strong connection between the theory and the computation. I mean, especially in linear algebra. I didn't want to call it linear algebra. I didn't want to teach linear algebra anymore. I wanted to teach matrix theory and make a distinction between the two. So I didn't want to teach abstract, theorems about vector spaces and axioms for vector spaces. I wanted to teach matrices and the singular value decomposition and the simplex algorithm. So I could use MATLAB, and that influenced certainly the last half of my teaching career, so that there wasn't this disconnect between the theory and the computation.
Now, coming to a close on this discussion, two final questions that I would just go around and ask everybody. Florian, if you could set up a large billboard, where would you set it up and what would be on it? What would be your plea about engineering to the world?
Ask somebody else first, I have to figure it out.
Sure.
I'd rather comment on something else before.
Okay.
Since I think what Cleve was talking about, you talked about levels of abstraction. I think if you talk about this, actually I should mention that I think one of the best lectures I ever heard in my life was with Christian Reinsch, which was with me. He's gone now, but I'm really very grateful that he was teaching that way. And he was teaching mathematics. He wasn't teaching computing to start with. So I think if you look at this example, and there are much more other examples, you can look at an application field. And then you discover that in this application field, it's interesting to represent certain things as matrices, and you may find out that eigenvalues are important. And then you can study the mathematical theory of eigenvalues and understand what an eigenvalue is and how you characterize it in mathematics and what are the properties, and can prove certain things about it. And then you can talk about algorithms to calculate eigenvalues, which is a different thing. It is related, but it's a different thing. And then you can talk about machinery, and then you can talk about real computers and how you organize a computation in a real computer. And these are at least 4 levels. And I would like to see students to understand how these 4 levels are related and what they have to know about these different levels and their relationship to solve problems. Maybe I should put that on a billboard.
Yeah. Which would be a very large billboard, but
billboard, yeah. Because as Cleve just explained, his ambitions of teaching singular value decomposition and the computations associated with that made me think of Gene Golub, who used to have a license plate for his car called SVD. So there was his vanity, or how you call this, vanity plate?
Yeah,
Vanity
plate.
Yeah.
SVD, singular value decomposition. And I think I like that a lot. That
It said Prof SVD.
Prof SVD,
Okay.
yes.
Prof SVD, his car said.
Yeah, and I would always then say add to this SVD, and this is what I tell my students at times, is that it's the Swiss knife of engineering. So computational Swiss knife, and if you forget anything from your math education in engineering, just keep the SVD in mind. It's a very, very powerful tool.
That's an interesting idea, to start promoting the SVD on billboards.
Yeah, why not?
Well, if it's on license plates, it could also go on billboards.
Sure.
My goodness. We could do that, couldn't we? How much does a billboard cost?
Well, I don't know.
Put one up. There's a, we have these, do you have these here where you have these signs along the road that sponsor cleanup, where companies sponsor a piece of the road? So we have one on Route 9 in Natick near MathWorks, where MathWorks sponsors a piece of the road, and it has the MathWorks logo on that. That's incredible. That vibrating L-shaped membrane is on the road. It's on a sign on the road, Route 9, Natick.
So you already got your billboard?
It's not a billboard. No, it's not a billboard. It's just a little sign. Yeah. Now you got me thinking bigger here.
Yeah.
See?
So if you think that people don't know what you're doing, maybe we should have a campaign going out. Did you get your SVD today?
But see, the membrane has to actually be vibrating.
Yep.
So this billboard has to be vibrant, has to be motion.
Sure.
Bubbly.
Oh my goodness, you got, okay. All right, we can get this, yeah. It's not an ordinary billboard, it's got a built-in MPEG player or something here.
Exactly. Good. And with that note, on a vibrating membrane on a billboard near your hometown anytime soon, I want to say thanks to you, Cleve.
That would be glorious to put that up.
I want to say thank you, Florian. Thank you, Klaus Diepold, and thank you, Manfred Breu. And thank you all for joining us today on Cleve's talk as part of the speaker series. Thanks a lot to the folks from the speaker series. And yeah.
Do you think my wife will let me do it?
I don't know.
If I get her that quadcopter with the Raspberry Pi on it, then maybe I can do the billboard.
You can get away with the billboard. Okay, thank you.